You may have come across these type of images. This is the world without the water. If the water is drained away, then it looks like this. The continents are given here in a yellow beige touch, and the submarine realm is given here in blue. And right in the middle of the Atlantic, we have this spine. There's a long mountain chain. It's not just in the Atlantic, it goes through most oceans of the world. It's actually a mid-oceanic ridge system. And this system is about 60,000 kilometers long all around the globe. And it was first discovered in the Atlantic that this kind of feature exists. And there we call it the Mid-Atlantic Ridge. It's actually a mountain chain, and 84% of all volcanoes on the planet are along these submarine ridges. So we always talk about big volcanoes on shore, but most volcanism happens actually under the ocean, underwater. So let's talk a little bit more about the Atlantic. Well, as I said, it is the second largest on Earth despite its young age. And I should perhaps put this in context. The United States is less than 1/6 of the size of the Atlantic Ocean. So it's quite a big, geographically big feature. And it's only formed as late as the Jurassic period. You all heard about Jurassic Park. This is when the dinosaurs were going strong. And this is indeed very important for us because, I'll come to that in a minute, there is actually similar dinosaurs on either end of the Atlantic Ocean, for example, in Africa and South America. And this was very strong geological evidence for fitting these together. We only learned about the history of the Atlantic very late, comparatively speaking. It goes back to this gentleman, Professor Wegener. He was one of the first to postulate that the Atlantic spread. And it started off probably quite simple. He looked at Africa and South America and realized you can actually fit them together. So you can formulate the hypothesis, well, if they fit together, maybe they were together back in the days. And you can start reconstructing things. And that's what he did, and he started to collect evidence. And after many, many years of collecting evidence, he concluded that indeed there must be some magic process that he called continental drift that separates continents over geological time. And by back projecting all of this, he realized that all of the major continents must have been in a single place or in a single mass some time back. He called this giant continent Pangaea, all of the Earth. And you can then reconstruct this, and maybe the numbers are a little small in the lower right-hand side. There we have 80 million years, 54 million years, 27 million years, and present day. So this is a projection through time. The top left one of these four shows 80 million years ago, and the lower right one present day. And there you see the continents were slowly starting to drift apart. And it started in the southern Atlantic, and then it, like a zipper, opened up towards the North Atlantic. Now, in science, it's been a pastime of many geoscientists to reconstruct plate motions, particularly over the last few decades since the discovery of plate tectonic phenomena. And here's a different projection of the same thing, focusing now on the North Atlantic. And again, there is ages given here, but this time the ages are given in color. And 0 means present day, and 200 million years is spot on in the Jurassic. And there you see the ocean was stretching, and more volcanic products are forming every day on the bottom of the ocean. And once they form, they spread out, and therefore the youngest rocks are actually at the Mid-Atlantic Ridge, and the older ones are further away. So this was a phenomenon that was discovered only in the late 60s, early 70s, that not only do we have a mountain chain, the mountain chain is actually a spreading center, which brings magma up, and then it pushes it to the side. Brings it up, pushes it to the side. And paleomagnetics, the study of magnetic minerals in old rocks, has been instrumental here. We not only can work out that there is magma rising up, erupting at the surface, and there must be a movement here, we can actually determine this with the magnetic polarity of the rocks. If you look at the ocean floor, and we have that spreading center in that small cartoon in the top right, and there's new magma forming over geological time, depending on the Earth magnetic field, the tiny little needles of iron ore that are in the magma, in the volcanic rock, they will orient differently. And that produces magnetic stripes. You can only see them with a magnetic survey. You cannot see them otherwise. But the ocean floor has these magnetic stripes. And that tells us that Wegener was right. It comes up and it spreads towards the side. And it must be doing so for hundreds of millions of years. So once we think about this spreading happening very early in the Jurassic, maybe with a small rift. And we have rifts like this today. In Africa, we have a rift. And the Red Sea rift is a little bit further advanced. And the Atlantic eventually is a full ocean there. We can come up with this model of initial breakup of a continent and increasing spreading of a continent. And while this is a beautiful concept, can we actually see that in reality? And the answer is yes, we can, because we can go to Iceland. And this is already advertisement for my next cruise, which is to Iceland. So if you're interested, come along. It's going to be later in July. And here in Iceland, we actually see the plates breaking apart. On the left of this particular image, you are on the North African plate, and a little bit to the right, you would be on the Eurasian plate. And there we have this large mid-Atlantic spreading area on the surface. So why is it on the surface? Why is that not something we see everywhere along the Atlantic, that we see these mountains reaching above the sea? Well, it's because Iceland is a bit of a special case. Not only does it sit on a spreading ridge, there's also a plume. We discussed plumes, these anomalies that come from very deep, these cylinders of material that push up hot material, and then they start to melt and produce magma. We discussed this for Hawaii and the Canary Islands, and Iceland has one of them as well. And there it intersects with this spreading area, and that's pushing the spreading ridge above the ocean surface for us to inspect. So here's a few impressions from Iceland. This is the literal plate boundary between Eurasia and the North American continent. And this is, of course, only visible because of the push from underneath, from the Iceland plume. There we have a coincidence of two very fundamentally different tectonic features that happen to be combined there. Now, and you can actually walk along this plate boundary, and you can walk, and eventually you come to the lower lands, not the highlands, but there you see it again. And eventually, if you were to continue to walk, you will find that it continues under the water, of course. And as I said, it's thousands of kilometers long. And in Iceland, you can go diving, and you can see these features underwater. So here's a few more there. The earth breaks really apart. And in many places, then, magma can actually rise up. Here are a few more impressions of how this spreading system looks near Iceland under the water. So obviously the scuba diver there can't go too deep, so we're pretty shallow at this point nevertheless. So the average depth of the Atlantic Ocean is of course a little more than those images I've just shown you, and the average is about 3,300 meters, and the captain said it today that we have about something like 3,500 meters below us. But in some places there will be submarine seamounts, as he referred to them. Of course, they're volcanoes, let's be real about that. And they may reach up to 25 meters below the sea. So you're actually going to go over volcanoes. And well, most of the time they're quiet, of course. And this is important. There is a very deep spot in the Atlantic. It's near Puerto Rico, and there we actually have a depth of about 8,600 meters. Can you believe it? So, but research on the mid-Atlantic is something that has been going on ever since the discovery of these features. And this is several research ships I had the pleasure of sailing on. I also put in some images in the top right and the lower left to make you feel a little better about the swell today, because I had some really rough days out there as well. So, but let's focus on some research here. Well, how do we know all these things? Well, partly initially it was sonar after the Second World War and radar, etc., that allowed us to an echo to determine where these mountains were. But initially, people were putting telegraph cables and all sorts of other kind of construction over this mountain chain, and people were surprised why they always ruptured in the same place. And that happened to be the Mid-Atlantic Ridge. Nowadays, we of course have submersibles. And well, in the Cold War, this has also been, of course, scientifically very important, although not all the data were always accessible. The US, the Russians, and whoever else had submarines, they were, of course, looking, what can we do with these submarine mountains? Can we use them to hide out? But then people realized hiding inside volcanoes is also not always good. So eventually it was decided that they're not good for submarine naval bases and things like that. So, but there is still a lot to be learned. Now, how do these volcanoes erupt? Well, they erupt along these cracks, these fissures. And it's very hard to observe them. So this is why I'm giving you an image here from Iceland. This is in 2022 in Iceland. This is the very, very start of the Meradalia eruption, very close to the Fagradalsfjall volcano. And there you can see that there's a wall of fire coming up, a wall of lava, and it's a crack that feeds them, very much like those cracks that we have in the submarine realm along mid-ocean ridges. Once magma erupts, well, it can't quite spew out in the same fashion as on continents. What usually happens is it starts to freeze on the outer skin. And there's a strange effect. It was discovered by Mr. Leidenfrost, the Leidenfrost effect. And what does it do? Well, you probably had the experience of having a water droplet going on a hot plate. And then the water droplet starts to dance. It doesn't immediately evaporate. It actually dances around. And that's the Leidenfrost effect. It's a thin, tiny vapor film that forms in between the hot plate and the water and actually insulates the water and allows the water to survive longer, to dance around on the hot plate. And that's what we see underwater as well. Magma often has a thin vapor film surrounding it, and this protects it. This allows that the lava can actually travel for quite a bit underwater. Because given the vast amount of water and the little bit of lava, you would expect that lava freezes immediately, but it doesn't. And that's because of this very special effect, which Mr. Leidenfrost discovered already in the 1790s, I think. It took us a little longer to realize that this is what happens underwater with lava as well. So, but let's dive into theirs literally. Well, not literally, figuratively. And here we have one of those cracks, and you can see the bulbous lava rock at either side of this. And there we're spreading this, and the spreading allows more and more lava to rise up. And here we have, well, a tongue of lava, and the lower machinery parts, that's from a submersible. And close to these sites, we often get a lot of venting of hot fluids as well. And depending on what the fluids are charged with, they come either as white or black smokers, as people call it. They're not smoking. There is no smoke underwater. This is actually precipitation of tiny little crystallites of minerals that are dissolved in these fluids. So the hot fluids come up, they have been heated inside the volcanic system, and once they hit the cold seawater, they will lose their load carrying capacity and they will precipitate a lot of tiny little crystals. From a resource point of view, the black smokers are a lot more attractive than the white ones because the black ones carry a lot of metals. And we'll talk about this in a few minutes later. So here's a few impressions of how the world under the water, the volcano world, looks like. So there we have these bulbous lava occurrences. We call them pillow lavas. And pillow lavas are a typical feature from the Leidenfrost effect. This is where, well, tongues of lava can migrate, but they're cooling on the outside. And here's fields of pillow lavas. Sometimes they break through, and then you get something like in the lower right, where you have a tongue coming out of a tongue, coming out of another tongue. So whenever the outer margin has frozen over, but the liquid is still, the interior is still liquid, then you may have a new tongue forming. And they have these radial cracks, as you can see in the top right, very typical feature, and this enables the geologist, even if you find this on land, to say, oh, these rocks formed underwater. Very characteristic feature. And of course, we can sample them now with submersibles most of the time. And these volcanoes are not just attractive for us as scientists, they're also attractive for submarine life because of the nutrients and because of the warmth. A lot of biota will actually flock to these areas. And these volcanic vents are, strangely enough, even if they are new, they get settled on very, very swiftly. So, here's a few more features. And, well, when the first images from submersibles came up from the top two sites, for example, there was initial discussion by the archaeologists, is there drowned cities down there? And there's pillars, there's roofs and things like that. But the reality is there's no such thing. These are all natural features. This is when you actually have a lava lake and you have a little bit of water caught underneath. The water rises up and it chills some areas, and that's where the columns form. The lava might drain away, and then you get these very strange constructions that look a bit like man-made structures at times, but they're not. And the evidence for that is in the bottom right. This is when you take one of these roof samples and turn it around, so that's the underside of the roof, and there you can see that the lava was actually pulled along. So this is a natural feature. So here, a few words about these black and white smokers. As I said, these are geothermal vents, and they're precipitation of all the tiny minerals that causes these chimneys to form. And the chimneys are actually, when it's a black smoker, very rich in metals. And we can, of course, study them. And sometimes you also get white smokers. They're very silica rich, so they're economically less attractive. But the white ones are very attractive for marine life. And as I said, there is a lot of marine creatures that love that area. And the most peculiar one I came across, and I'm not a biologist, is this kind of set of beasts, if you want, the archaeobacteria. So the biologists say they're not really bacteria, they're even more primitive than that, but I don't want to go into the details here. There has been extremely simple forms of life detected there that feel extremely happy at 190 degrees Fahrenheit. So they live there super happily. They get energy from breaking down various minerals, and they love sulfur, is my understanding. So they can live there, and they can cope with acidities down to 0.9 pH. That's pretty acidic. And they live there. So some people even argue this could have been the very origin of life, these submarine volcanoes there. So now we looked into the center of the Atlantic, but we should also look at its margins, because the center, well, I think we get the idea. There's spreading there, and the Atlantic spreads rather slowly, only a few centimeters per year. But what about the margins? Well, first of all, around the Atlantic, we have dominantly what geologists call passive margins, meaning not a lot happens there. We have, well, the spreading center in the ocean, and it spreads and spreads, but the continental margins are not affected. They're actually sitting there passively, hence the name. But every now and then, one of these passive margins starts to get a little unstable, and you could have landslides from there. So sometimes you get very big landslides. And there was a big landslide recorded, or well, we didn't record it, it happened a few thousand years ago, but you can see the evidence from this off the coast of Norway. There's the Storegas landslide, and it was a big, big landslide. You can see the map here. In red, you get the deposit. So a big chunk of this passive margin broke off, and it likely covered a large area with a wave, with a tsunami wave that it caused, and the collapse is estimated to have evolved, in this case, 290 kilometers of coastal area that simply collapsed into the sea. a massive tsunami is supposed to have happened, and you can actually work out the thickness of the tsunami sediments in various places all around Scotland, Shetland, and Norway, and that's the blue dots on the map. People have done the research there, and from the thickness of those you can actually work out where the tsunami came from, etc., etc. So that's passive. As I just tried to point out, they are called passive, but they're not always passive. Sometimes this is very unpleasant. We have none of the such landslides witnessed in, well, recent historical times, but that's not to say they can't happen. Another intriguing feature is that if you look at the Pacific is surrounded by subduction zones. What are those? Well, this is when you have an old plate and a young plate, and they meet. The old one tends to be denser and heavier, and the one is then shifting above the other, and the old one usually subducts it back into the earth. This is something that mature oceans do, like the Pacific. It's got this all around. It's called the Ring of Fire. But the Atlantic has virtually none of those features. And the trick here is you need a certain age of ocean crust in order to do this. If the age of the ocean crust is about 180, 190 million years old, then the weight of the crust becomes so heavy by itself, because it's cool, it's dense, it's heavy, it will start to sink by its own weight into the mantle. And we said the Atlantic only formed in the Jurassic. And that means that most of the ocean crust in the Atlantic is not yet of age to subduct by itself. There's one or two places where the age is just about getting right, and this is here in the Caribbean. We have the first little subduction zone of the entire Atlantic Ocean forming in the Caribbean. Now, scientifically, this is wonderful. From a volcanological point of view, it does make some very unpleasant volcanoes. We had the 1902 disaster in Martinique and Saint-Pierre, and killing 30,000 people. So this is a different type of volcanism. It's more aggressive. And scientifically, we don't have to go into the details, but scientifically, this is a unique situation for geologists because we can actually study the formation of new subduction zones. So this is how baby subduction zones are born and how they evolve. And this is, of course, something that is valuable to us. Hence, I'm showing you this diagram on the right. And we don't need to have the details here. What it means is that the old crust of the Atlantic is suddenly getting subducted under the younger material that sits close to the Central American part. And then you get little volcano islands above that come from material that is expelled from the downgoing slab. Now, we talked about mid-ocean ridges now and subduction zones. There's only one major tectonic environment that makes volcanoes that we haven't really touched today very much upon, and that is plumes. And the Atlantic is actually littered with plumes. It sounds kind of special, like Hawaii and the Canaries, but if you look very carefully, the Atlantic has a lot of little plume-related islands. So this is from one of our articles from a few years ago. This is on the part of the world we're in. There's the Madeira archipelago, the Canary Islands, there's the Cape Verde Islands, there's the Azores. And if you go further down, then you'll see that, well, the oceans are all full with these. In the lower right-hand side, you have a diagram, and all the little yellow-red dots are actually plumes and related submarine or above the ocean chains of islands that connect to plumes. And just to bring you back to the Canaries for a second, although we're just about leaving, there we see the ocean magnetic anomalies, the yellow stripes, and we see the ages of the islands, and they cut across the ocean stripes. So that means the mid-ocean ridge has nothing to do with their formation. This has to be a plume that sits stationary and the plate is moving above. This is also very common in the southern Atlantic. There we have Santa Helena, for example, and Santa Helena connects to a plume chain as well. And then we have the Whalefish Ridge, we have Tristan da Cunha and Gough Island and all these places, Ascension Island, all of them are plume related. So let me bring you to this place here. There's Tristan da Cunha and Gough Islands, and there is a whole submarine chain of little volcanoes that goes all the way to Africa. And you actually have the same thing on the other side, and it goes all the way to South America, supporting Mr. Wegener's idea that those were actually once together, these continents, and there was a little volcano in the middle, and it's been going on ever since, and you can see the string of volcanoes on either side. So let me bring you back to the North Atlantic, and that is here we also have more of those intersections. I talked about Iceland being a bit of a double player. It has a plume as well as a ridge, and this is also the same for the Azores. On the left-hand map, you see the Canary Islands in the very bottom left, and the little dots there are earthquakes. The bigger the dots and the more they get colorful, the more intense the earthquakes are. There's actually surprisingly few earthquakes in the Canaries. But when you look along plate boundaries and spreading centers, then you get a lot of earthquakes. And the plate boundary between the African plate and the European plate, that's the large number of earthquakes sitting on the top of the left-hand diagram. And you can see them all around the mid-Atlantic ridge and going to the Azores triple junction, ATJ labeled there. And this is where three plates meet, a very special place. This is where the European plate, the African plate, and the North American plate actually meet. There's one triple junctions. And of course, we get volcanoes there. Wouldn't be right otherwise. And that's the Azores. The Azores are a little different because, again, they have different features. So the Azores tend to be more elongate because they sit on these plate boundary fractures. The Canaries are not. And there's a few differences like this. And one crucial feature is there's a lot of earthquakes in the Azores, really, really bad ones. Unlike in the Canaries, earthquakes are not the key problem. And just yesterday, I got news, one of the little Azores islands is starting to rumble. So maybe I have to go to the Azores very soon. Let's see. So, but having talked about this, I want to bring this together before we go a little bit further in our considerations. Two more points to tackle. But here we have now rift systems, spreading zones, plumes, and subductions. These are the key features that make a properly grown-up, mature ocean. And the Atlantic is very young in this context. We have only one tiny little bit, and I don't like this pointer, but let me see whether I can make it work. Here we are. There's one tiny bit of subduction. These little strings of triangles, that's subduction zones. There's only one tiny one forming here at the margin of the Atlantic. Looking at the Pacific, well, it's got this all around. The Pacific is a properly grown-up ocean. The Atlantic is just becoming about, well, it's just getting its driver's license soon.